Let's go over problem number 2 on buffer solutions from our day before the 2-day quiz practice problems. Now this buffer problem, we have a buffer because we have a mixture of hypobromous acid, a weak acid, and we have hypobromite ions, which would be the conjugate base or ions that would be in the salt coming from that weak acid. This mixture would give us a buffer system. When we go to calculate the pH of the buffer, we can still write out the equilibrium for the weak acid in water. And that'll be our reaction that we'll write. So the reaction we have, our R in the Rice strategy, would be the weak acid, HBRO, hypobromous acid, reacting with water to give us hypobromite ions and hydronium ions. This will be the reaction for our buffer system. In the problem, we're given the concentration of our weak acid initially as 0.20 molar. This gives us our initial value for the acid. And we also have the initial concentration of our salt ions, 0.250 molar hypobromite. And initially we have 0 for the hydronium. Because we have 0 the hydronium, this will be plus, this will be a plus, we have minus, it's going to be X, X, and X because we're in a 1:1:1 ratio. We now have our equilibrium values, and because our X here is so tiny, we'll be able to drop off the X for our purposes of calculations. We can set up our Ka expression, and now we can substitute in our equilibrium values into the Ka expression. Solving for X will give us our hydronium concentration. Our hydronium comes out to be 2.08 times 10 to the negative 9th molar, which gives us a pH for this buffer system of 8.68. For the next part, we're given in the problem, the beginning we have 0.200 molar hypobromous acid, and we have 0.250 molar hypobromite ions. Our sample size is 0.500 liters. We're going to take and remove a 0.075 liter sample of this buffer system. And it's asking, in this sample now that's only 75 milliliters, what's our number of moles of hypobromite ions and hypobromous acid? For the hypobromite ions, we can set up a proportion. We know we have 0.250 moles per 1 liter of hypobromite ions, so we're going to have X moles present in 0.075 liters. Solving for X gives us 0.01875 moles of hypobromite ions present in our 75 milliliter sample of the buffer. Repeating the process for the hypobromous acid. For the hypobromous acid, we know we have 0.200 moles per 1 liter, so that means we're going to have X moles present in a sample that's 0.075 liters. Solving for X tells us that we have 0.015 moles of hypobromous acid present in our sample that's only 75 milliliters in volume. The next part here has to write the chemical equilibrium equation for the buffer system. This will just be the reaction of the hypobromous acid with water, something we're quite familiar with at this juncture. This would be the reaction for our buffer system. It's the same reaction that we would write if it were for the weak acid hypobromous acid with water. Now in the next part of the question here, it says we're going to add 5 milliliters of hydrochloric acid to this buffer sample. Adding hydrochloric acid is going to cause the hydronium concentration to increase. The hydronium concentration increases. To alleviate the excess hydronium, the buffer system reaction would shift to the left to consume the excess hydronium, turn that back into weak acid molecules, and have the amount of salt ions decrease slightly when we shift to the left. This will allow the amount of hydronium ions to remain relatively constant and keep the pH relatively constant. The next part of the question asks us to find how many moles are present of HCl in that 5 milliliter sample of the 1 molar HCl that we're adding to the buffer. The 1 molar HCl lets us set up a proportion where we know we have 1 mole of HCl per 1 liter, so we can find out we have X moles of HCl present in our 0.005 liter sample. Solving for x gives us 0.005 moles of HCl are being added to our buffer. To calculate the pH of the buffer sample after we've added the HCl, we'll utilize the Rice strategy. Our reaction for the hypobromous acid hypobromide ion buffer is the same as we'd have for the weak acid. That's our R value in the Rice strategy. The next part for buffers is something unique to buffer systems. That is, for buffers only, we can do the equilibrium using moles. What this means is for buffers, because we have a ratio of salt and weak acid present, we can utilize moles when we use our Rice strategy for our initial, our change, and our equilibrium values. Earlier, we'd calculated that in our 75 milliliter buffer sample, we have 0.015 moles of hypobromous acid, and we have 0.01875 moles of hypobromide ions. These are our initial values of these prior to adding the addition of the HCl. When we add the HCl, the H3O plus concentration will increase. That's going to drive our reaction to the left. So for the change value, the amount of acid is going to go up, the amount of salt is going to go down. The size of the change is the number of moles of HCl that we add to our buffer system. Earlier, we determined we were adding 0.005 moles of acid, so as our reaction shifts left, the amount of change is going to be 0.005 moles up as we shift left, and the amount of salt is going to go down by or minus 0.005 moles. At equilibrium, that'll leave us with 0.020 moles of hypobromous acid, 0.01375 moles of hypobromide ions, and the hydronium will be X, and that the hydronium will be whatever it needs to be once the equilibrium shift has been completed. We can now take our equilibrium values of hydronium, hypobromide ions, and hypobromous acid and insert them into our Ka expression, and then we can solve for X. When we get X, that'll give us our hydronium concentration, which we can use to calculate the pH. Solving for the hydronium, we get X is 3.78 times 10 to the negative 9th molar, which gives us a pH subsequent after the addition of the HCl for our buffer system of 8.42. The next part of the problem says we're going to add sodium hydroxide to our buffer system. The buffer system, again, is the equilibrium for the weak acid hypobromous acid plus water. When we add hydroxide ions, the hydroxide ions are going to react with the hydroniums to create water and water. That's going to cause the hydronium concentration to go down. In response to that, the equilibrium, to replace the hydronium ions that have been taken away, the equilibrium will shift to the right in response to the sodium hydroxide addition. To calculate the moles of NaOH that we're adding to our buffer, because this is a solid sample of sodium hydroxide, we'll use the molecular weight or mass of 1 mole that we get from the periodic table. 1 mole of sodium hydroxide is 40 grams, which means we'll have X moles of sodium hydroxide present in our 0.120 gram addition. Solving for X gives the size of our sodium hydroxide addition to be 0.0030 moles sodium hydroxide. The next question wants us now to calculate the pH of the buffer solution after we've added the sodium hydroxide. Now, once again, for buffer system, we can use buffers only. We can use moles when we use our Rice strategy. Earlier, we determined the amount of moles that we have of our hypobromite and hypobromous acid in a 75 milliliter sample of this buffer. We'll use those again. Earlier, we determined a 75 milliliter sample had 0.015 moles of hypobromous acid, and we had 0.01875 moles of hypobromide ions present in the 75 milliliter sample. When we add the sodium hydroxide, that's going to cause the hydronium concentration to go down, so our reaction will respond by shifting to the right. That means the change value for the acid is going to be a negative, and for the hypobromite ions, it'll be a positive. The size of the change will be the number of moles of sodium hydroxide that we add to the buffer. We determined that we were adding 0.003 moles of sodium hydroxide. That gives us the size of our change, and now we can get our equilibrium values. We now know that we have 0.012 moles of hypobromous acid, 0.02175 moles of hypobromite ions. The amount of hydronium will be X. As the hydronium gets established, once the equilibrium is done shifting, it needs to be X to just let it be equal to the equilibrium constant once everything's done shifting. We can now take our equilibrium quantities, put them into the Ka expression, and X will give us our hydronium concentration once equilibrium has been reestablished subsequent to the addition of the sodium hydroxide. Solving for X gives us a hydronium of 1.43 times 10 to the negative 9th molar, which leads us to a pH for this buffer system of 8.84, which is what the pH is after we've added the sodium hydroxide to the system and the buffers responded to that sodium hydroxide addition.